And we're ready to go. So the slide I have up here. Oh, first of all, did anybody have any questions? Obviously, we didn't get very far yesterday, but I'm going to just be trying to continue from where we were. And we looked at very few examples. So basically, I want to add more examples and firm up techniques today. Did anyone have any questions from last time or before? So we'll get started. This is the last problem I showed you yesterday. And there's kind of a general technique here. In fact, so much of a general technique that I kind of made a template. But first, let's just look at the problem from yesterday. And I made this one up, but it was basically if you have a sphere and you're in the process of inflating it, and you're told that the right now the radius is increasing at a rate of 3 per whatever, let's say 3 inches per minute or 3 inches per second, I don't know. And right now, at this particular moment, the radius of the balloon is 4. Then what's the rate of change of the volume? That's basically the question on the top. And so immediately you have to identify your variables. We're talking about volume of a sphere, and how can I relate that to the only other thing given, the radius? Well, we would have to know the volume of a sphere, which is shown here as V equals 4/3 pi times r cubed. The next step, once you've got that relationship in your variable set, then you differentiate the whole thing with respect to time, because we're talking about related rates always deal with time. So notice the notation or derivative with respect to time out here on the far left. So we do what we've learned before, implicit differentiation. So we find the derivative of both sides. So left side, dv dt, right side, well, first do the power rule, bring the 3 down, 3 times 4/3 is 4. Pi is a constant, stays the same, and reduce the power on the variable by 1. But because r is not e, we need to still do the chain rule and times dr dt. The final step is use the given information at the top, substitute in, and find what you're supposed to find. We were supposed to find the rate of change of the volume, dv dt. That's cool, because that's already by itself on one side of the equation. So we just plug in what? R being 4 and dr dt being 3. So the substitution line down there. So basically, this is the substitution line right here. And then just simplify, and we've got it. So what rate is the volume changing with respect to time? 192 pi cubic inches per second. Okay, so that's that general template may seem kind of corny, but I've created, this is a template that I've used in the past with calculus students. And, I'm not very clever on coming up with acronyms, but, I've got identify variables, relate the variables. That's the equation that brings the variables together. And then C, use the chain rule to implicitly differentiate. And then lastly, substitute and solve, IRCS. So this little template, I don't know, might be something you want to adopt, because in the past, students have thought related rates are kind of tough. But I think this helps you organize your information and at least have a nice solid plan instead of whoa, where do I start? Often is the reaction on these. So let's use this template and let's go through some of the problems in the book. That's the plan for today. So the first one I'd like to do is number 2 in the book. Make sure I'm going to head over back to the okay. Interesting. That doesn't look like number 2. But anyway, the problem they give you, was I looking in the right place? Using related, oh, I actually wound up doing number 1. I see it there. Okay, sorry, it's labeled wrong. Okay, so now I see, so let me change that. That's number 1. Okay, so you'll see they give you a bunch of information. They tell you the equation. So this time they gave you the equation y equals square root of x. We've got 2 variables, x and y. And they gave us dx dt is 3, and they said x is 4. So that's all basically given information in those beginning problems that kind of hand it all out to you. So, I mean, you don't really have to develop, but there's the given information. So the next step is to use the chain rule to differentiate it implicitly with respect to time. Now, I rewrote the square root of x as x to the 1/2 power. And we're going to differentiate that whole thing with respect to time. So the left side is just dy dt. The right side, we use the power rule. Exponent comes down 1/2. We keep the variable and we reduce the power by 1, x to the negative 1/2 power. X is still not t, so we have to do the chain rule, dx dt. So then I just rewrote it using root notation. 1/2 x to the negative 1/2 could be written, like this. 1/2, and then the square root of x is on the bottom because of the negative power, and then times dx dt. Okay, so about as far as we can go with the differentiation. We don't know even what we want to solve for. I should have written that down. Let's go back and look at the problem. It says find dy dt. So, I really should put that on the top here. So let's, way up at the top, I could have added dy dt is what we're trying to find. Good. So the equation is nicely solved already for dy dt. So now it's time to substitute and solve. And in this case, this is really easy. Dy dt, x is 4. The square root of 4 is 2. And 2 times 2 is 4. So we wind up with 1/4. And then multiply that by dx dt, which was given to us, is 3. And pretty simple. We're done. So what is dy dt? 3/4. So, those very first ones, there isn't really much to analyze. It's pretty straightforward. We got I think I've got one more of those where there's really nothing to analyze. You just kind of go ahead and plug it in. And that one that I have down is 6. Let's see if I've picked out the right problem this time. Yeah, and I put an A there. So number 6, we scroll down a little bit in the book. It says y equals 1/x squared you're given that dx dt is 6 inches per second, and then there are actually 3 parts to it. I'm just going to do the part A, different values of x. When x is -2, so we're going to do the part A. So that's, and we are trying to find, if you look up here in the top, we're trying to find dy dt. Okay, so let's go back. So I should have put that one more time. It's always good to also put down what it is they ask you to find. Also, they gave you the equation. So again, we didn't have to figure that out or reach back into our memory bank. They said y equals 1 over x squared. And I just, rewrote that to make it a little bit easier to do derivative work. 1 plus x squared to the -1 power. So now it's time to move on to the differentiate implicitly stage. So find the derivative of the whole thing with respect to time. So the left side, dy dt, the right side, first we do what? The outer, the power rule, bring the -1 down, keep the base, 1 plus x squared, the same, reduce the power by 1. Now the power becomes -2. This time we have, the first chain rule is, what's the derivative of 1 plus x squared? Well, that's 0 plus 2x. And then we need to do the chain rule one more time because x is not t. So, watch out for this part. People might have a tendency to forget. We do need to do that. All right. And then I rewrote that. Again, getting rid of those negative powers and going back to, without negative powers way of writing it. So I rewrote it. The -1 I passed off onto the top. So 2x is now negative. -1 times 2x. And the 1 plus x squared to the -2 power is 1 plus x squared to the +2 power on the bottom. So just a little bit easier format for that derivative. And then it's time to substitute. So now you go look way back at the top. We've been given dx dt. That's 6. And we know what x is. It's -2. So you plug it in. What's -2 times -2 is a +4. On the bottom, -2 squared is 4. 4 plus 1 is 5. And 5 squared is 25. And then just do the arithmetic. So what is dy dt under these conditions? 24/25. So, any questions so far? It gets a little bit more challenging. I mean, typically these problems are written in word problem format, and so this top stuff has been kind of handed to us on a silver platter so far, and may have to do a little more digging as we move on here. All right, let's go on to, I think the next one I've chosen is number 14. And again, I failed to write down what it is they want us to find. So let's take a look at number 14. Here it is. A spherical balloon is inflated with gas at the rate of 800 cubic centimeters per minute. Okay, so we've been given a bunch of things already. It's a sphere. So we're probably going to need the volume formula for a sphere. And we already know what? The rate at which it's being inflated. 800 cubic centimeters a minute. So that's actually what? dV dt. The rate the volume is changing with respect to time. So dV dt is 800. And you'll notice I wrote that down. dV dt equals 800. Oh, I do have one. They're trying to get us to find dr dt. And at the moment, R equals 30. Let me just go back. Do you see that? So it says, well, I'm doing part A. There's a part B too. Okay. So again, I'm doing part of the problem, and you guys can duplicate the same thing with a different R for part B. All right. So here's our variables and what we've been given. So now, I'm just saying we know the radius, we know the volume, and that's it for variables. And now here, you got to go a little bit back into your memory, maybe to your geometry book. We're talking about the volume of a sphere. So this you have to come up with yourself this time. They didn't give it to you. But, I mean, these aren't going to be hard. They're going to be pretty basic ones. So anyway, there's the volume of a sphere. 4/3 times pi times r cubed. Okay, so you know what's next. Next, we have to take the implicit derivative with respect to time. All right, we know how to do this. In fact, I think we've done this very formula before. We did it yesterday. So on the left side, dv dt. On the right side, we do the power rule. 3 comes down. 3 times 4/3 is 4. Pi is a constant, stays the same. R, we read the variable by 1. But because r is not t, we need to do dr dt, chain rule. Okay? So now it's just a matter of substituting and finishing. So for dv dt, that was given, 800. R is 30, so I can, for r squared, I'm going to take 30 squared, which is 900. Pi is a constant, that stays there. And dr dt is the only thing we don't know, so we have to leave that be, dr dt. So simplify, 4 times 900 is 3600. So that's 3600 pi there. And then divide both sides by 3600 pi. You would get, the raw answer you would get would be right here. And then I ran out of space, so I moved to the left there. Simplify that a little bit. 4 goes into both of those. 4 goes 800 2 times. 4 goes into 3600 9 times. So 2 over 9 pi would be dr dt. And you don't ever want to put a decimal in for pi. So please don't give me a decimal answer in a problem like this. This is the way you want to leave it be. So does anybody have a question on number 14? By the way, if you look at these, that template I made, that IRCS, if you have trouble remembering that, just remember maybe that your calculus teacher irks you. IRCS irks. Yeah, that was accidental, but anyway. I think these steps will help you. Okay, let's go to number 16 next. Not hearing any questions. And let's just take a look at it. See, typically you're going to have to look at it in the book. Hopefully this is big enough that you can see it, or you have your book handy. 16 says surface area. Surface area. So that means the area of all the surfaces on the outside. And this is area, not volume. All edges of a cube are expanding at a rate of 6 centimeters per second. So they're giving rate. Right? And if we call the edges E, they've given you dE dt. dE dt equals 6. You'll see I wrote that down right here. dE dt is 6 inches per second. How fast is the surface area changing? If I call surface area S, they're asking you to find ds dt. And once again, they give you two parts. When an edge is 2, when an edge is 10. I'm going to do part A, when the edge is at the stage of being 2 centimeters long. So they're giving you E is 2, and they're asking you to find ds dt. So see how we pretty much have the variables and what's been given and what we're supposed to find up there on the very top. That's always the first step. So now we need a formula for the surface area of a cube. Have you given a little thought to it already? I mean, what's a cube has how many sides to it? You got 4 going around and then a top and a bottom. So there's 6 of them and they're all identical, right? In a cube, they're all squares. And I mean, they're based on edges, isn't it? I mean, what's the area of a cube whose, what's the area of a square for when the side is E times E, or E squared, and there's 6 of them. So here's my surface area formula for a cube. Now, here's a case where we just had to kind of come up with this. It didn't take too long to figure it out. I mean, probably nobody has that memorized. Maybe you do. But anyway, so now it's time to, the old implicit differentiation. And we got to do it with respect to time again. These are rates. So the left side is just ds dt. And the right side, we first use the power rule. 2 times 6 is 12. E, reduce the power by 1. And then we have to do the chain rule, dE dt. So pretty simple implicit differentiation here. So now let's just do our substitute and solve. And we should be in pretty good shape. So ds dt, well, that's what we're supposed to find. E is 2, so I can plug in 12 times 2 is 24. And dE dt was given to be 6. So all we got is a little multiplication here, 144 square inches a second. So if the edges are changing at a rate of 6 inches per second, and currently the edge is at 2, so in a second, how much has the surface area increased? And the answer is the rate is 144 square inches per second. Any question? So this next one, quite a bit more complex. These have been nice and straightforward. Let's move on. I've picked number 18 to be our next problem. Okay, and let's read it. Depth. It says we have a conical tank, so a cone-shaped tank, and it says with the vertex down. It would make sense. It's 10 feet across the top and 12 feet deep. So already I made a little picture here. It's really crude, but up in the top right corner, we've got this cone-shaped tank. It's 10 feet across the top and it's 12 feet deep. And then what I was sketching in blue is, as this thing starts filling up, that blue circle is kind of what the height of the water is as you're filling it up. Okay, let's go back and continue reading. So 10 feet across, 12 feet deep. Water is flowing into the tank at a rate of 10 cubic feet per minute. So that's really what? dV dt. The rate that the volume is changing over time. dV dt is 10. So let's go back. Yeah, dV dt is 10 cubic feet per minute. So we've been given that. And we've been told that find the rate of change of the depth of water when the water is 8 feet deep. So I had to call this height something over here, the height of the water. See this crude H over here on the far right? Way over here. Sorry, I was pointing at the wrong screen. So I called it H. Okay, so the height of the water is 8. And what we need to find is this dH/dt. What's the rate of change of the height? Okay, now I'll explain what this R is in a minute. R is the radius of the circle on the top of the water. So you see that this circle I've drawn over here. I gotta think. I should be. Yeah, you just can't see it when I do it here. Anyway, this little blue. Yeah, I don't think you can see me drawing. But the diagram at the far right, you see that little blue circle? That's supposed to be the current top of the water as the tank is filling up. And R is the radius of that. Why do I need to know that? Because, okay, the volume of the water, would you agree, is going to be a cone. So as this pool, this blue pool goes up, we've basically got a cone of water. What's the volume of a cone? You guys remember that one from geometry class? I mean, one way to remember it, it's the area of the circle times the height times 1/3. Okay, so let's expose. So here's how I wrote that. Pi r squared h, that's the circle area times the height of the water times 1/3. That's the volume. So that one might have been a little bit, you could have looked that one up. Okay? But you notice we need the radius. Well, nothing up here is given anything about a radius. Okay, so I had to do some reasoning here. Let's see, do I have it on? I think I've got it on the bottom of the screen. So, yeah, take a look at this picture at the bottom. I've enlarged our cone, okay? And when you look at the whole thing, it said the distance across the top was 10. So that's the diameter. So now I know that the radius at that point is 5. And the height of the cone is 12. So I know. So you see we have what we have here is a right triangle, and we've got, and the thing is, no matter what height I am, if my water is lower, all those triangles have to be similar because they all have a right angle and they all have the same angle down here at the vertex. So because they're all similar, the ratio of the radius to the height has to remain constant. And that's what I'm doing down here. Radius to height is 5/12. Or we could just solve for R and say R equals 5/12 H. So I know you're wondering, why do I have R up here? Because I need it in this, I need it in my volume of a cone formula. Okay, so I don't have, the problem is, so I figured out what R is when you have the full thing. I just did, here, let me go to the next page. No, maybe I don't show it there. Okay, so I'll just do it on the bottom here. So what I said is, all right, I know it's 5 to 12. And I know the height, they gave that to me, that's H. So that should allow me to find the radius. And then when you cross multiply, you get 40 equals 12H. I'm sorry, 12X. And then X equals 40/12, which can be reduced to Did I do that wrong? So if you reduce that, what can we do? 4 into each? It would be 10/3. Yeah. So now I know the radius. So do you see where I got this from up here? I'm not sure we really need that, but I just wanted to show you. So even though they didn't give that to you, we were able to figure it out. So I was thinking, oh, cool. Well, then let's just do the derivative. Let's just do the implicit derivative with that formula. But then I realized there's something we don't have. We don't have dr dt. They didn't give it to us. You can't have two missing things. I can't have dh dt missing and dr dt missing. So even though I figured out the radius when this whole tank is full, I still can't solve it that way. So what I've got to do is just take this relationship we figured out here on the bottom. Whoops, excuse me. This relationship right here, way on the bottom there, r equals 5/12h. I need to use that to rewrite this problem so I don't have an r and it's all in h's. So I substituted for r 5/12h. You see how I did that right here? So all I did right here is rewrite the volume formula, putting in 5/12h where there was an r. Okay, so now, because I know what I'm supposed to find dh dt, and I know what h is, so now I don't have anything missing. So finally, we can go to the C step, which, by the way, I didn't have enough for, so I'm doing one on the next page. But now we can take the implicit derivative with respect to time. So let me pause here before I go to the next page. Hopefully you're following what we're doing here. So this one, we just had to do a lot of groundwork to figure out, wait a minute, how do I find the volume of a cone? And, well, for a cone, I need r, but I don't have r. And we've gotten through that. I hope you can see. We had to use some of our geometry and algebra skills in order to do that. So now we've got the equation we need. So now I needed the space, so I went onto this piece of paper. So here again, I made the substitution that we were talking about on the last page. I put in 5h for r. So then when you square it, you get this. And then you can put that together. 25h squared times h is 25h cubed. And you can even do put the 1/3 on the bottom. And so that brought me down to this stage, and I even simplified it to this. So I pulled the 25/432 off to the left as part of the constant. So, I mean, this is all constant right here, isn't it? Pi is a constant, so is 25/432. Yes, go ahead.
Why is it cubed?
Because, yeah, if you look at this step, you see how we had a 25h squared here?
Yeah.
But then I had to multiply that by another h. That's why it became cubed.
Oh, okay.
Yeah, anybody else? Thanks for asking. So we're finally able to do the implicit differentiation. So now we get into that, all right? So dv dt, I mean the derivative of volume with respect to time, okay? On the right side, so we've got this, I mean, we got a power rule. So I took the 3 down and multiplied it by 25/432. So 3 times 25 is 75. Keep the constant the same, pi. Reduce the power by 1, and then chain rule dh dt. So we've got that wasn't very hard once we got it simplified. And now substitute And now if you can remember, we were given some things here, right? I know. Here, let's just take a quick peek back. What were we given? We were given that dVdt is 10 and h is 8. dVdt is 10 and h is 8. So notice I plugged in a 10 for dVdt, and for h I plugged in, an 8. 8 squared is 64. I tucked the pi in the numerator here, but I mean, it's the same thing. And then basically I just did a bunch of arithmetic to get this simplified. So, I divided both sides by 4,800 over 432. That flipped it upside down on the right, and then I did some simplifying, and I came up with, finally, what they asked me. What was dH dt? And again, when you get a pi in answer, you really want to just, I can see I could have done better, right? 3 divides into both of those. So I could have said, nine over 10 pi is how I should have ended it up. So that one took a lot of horsing around, but really it wasn't calculus horsing around. It was all this, we had to find, all of this problem was created really by this guy right here. I mean, that's the only thing we had for the volume of a cone. And we had to have R in there, and we didn't have it. So we had to do this. We had to do some geometry down here in the bottom right of the screen and similar triangle thinking in order to figure out a way to express R in terms of H. And we were able to do that. And then, all right, now I can come back and make it an all. I don't have an R anymore. Now I've got all H's, and then we were able to proceed. Why did I have to get rid of R? Because even though we could calculate R, in fact, we did up here at the top of the screen, we didn't have the RDT, so we'd have been stuck. So we didn't have much choice there. So sometimes you'll run into geometry, arithmetic, mostly geometry stuff that you have to rely back on in order to get your formula in the right condition so that you can actually do this implicit differentiation. So anybody else have any questions? So it's pretty typical, this section on the right side of the page here is pretty typical for, let's see, let me close that up and make this a little bigger. These problems over here on the right are pretty typical for the related rates problems. You are given a word problem, and sometimes they'll give you the form, like you see here down here in number 17 they said, hint, the formula for the volume of a cone, oh, by the way, there's the formula I just used in problem number, 18. So sometimes they'll just tell you. But anyway, you've got to do the geometry and whatever in order to get this into a form so that you can really execute the implicit derivative. Okay, so let's go back and so anyway, this template, I don't know if you see any value in it, but I think at least it helps you kind of get things rolling. Divide it up into pieces, and I think once you realize what the pieces are, it's not too hard to follow through on them. It's pretty, it's actually lower level math in most cases. When it comes to the assignment for 3.7, what does he have here? It's this section right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 problems. So I think you should be ready to get going. I know we're done a little bit early today, but we just didn't quite have enough time to finish this up yesterday. Questions? All right, if not, then I think we're going to wrap it up. Thank you. Thanks for participating. Enjoy the beautiful sun, and have a good day.